Now we'll be discussing Article 27.6, that is electrical power. This is the last article of the chapter, and then we will move to magnetism. In this article, let us suppose that we have a charge that is moving from point A to point B, and the potential at point A is VA, and the potential at point B is VB. And we also consider that VA is greater than VB. So the electric field is from A to B. If the charge is moving from A to B, then the electric field is doing some work which is given by the value dW, and we can write this as dW is equals to dQ into VA minus VB. Now this work will be positive if the charge is positive, and the work will be negative if we have a negative charge. Now let us divide both sides of equation number 1 by dt. And now if I divide the left hand side by dt, I get dw over dt, and here I get dq over dt into va minus vb. Now this is work per unit time, and work per unit time gives us joules per second, and joules per second is the unit of power. So unit of power is also known as watt, and the bigger unit for power is horsepower, and we know that 1 horsepower is equals to 746 watts. So I can write this left hand side as P. This P is for power now, which is equals to dq over dt into Va minus Vb. We also know that dq over dt is equals to current, and P is equals to IVA minus VB, which may be written as V, or we can write it as delta V. And this is how the equation is written for power, that P is equals to IV. Power is defined as current into potential difference applied. We can also write this equation 2 as, if I replace V is equals to IR, then I can write P is equals to I square R, or if I want to replace current equals to V over R, then the power will become V square over R. So unit of power is joules per second, as told you before, and this is also known as watt. Bigger unit of power is horsepower, and 1 horsepower is equals to 746 watts. Now we will be solving some related problems to power. In example 27.7, the statement says an electric heater is constructed by applying a potential difference of 120 volts, that is V will be 120, to a nichrome wire that has a total resistance of 8 ohms. R will be 8. Find the current carried by the wire and the power rating of the heater. So the data given is VR, and we are to find I and P. So we'll proceed as first by using Ohm's law. We will find current, that is I is equals to V over R. Putting in the values, we get 15 amps. And now to find power, P is equals to I square R. We have the value of I and R, and get power equals to 1.8 into 10 raised to the power 3 watts, that is 1.8 kilowatts. So it's a very simple problem using Ohm's law and the formula to calculate power using current and resistance. Next is example 27.8. It has two parts. In part A, it says what is the required resistance of an immersion heater that will increase the temperature of 15 kilograms of water from 10 to 50 degrees Celsius in 10 minutes while operating at 110 volts. If you look at the data and you remember heat and thermodynamics, you see that there we have mass and change in temperature and time. So we will be referring to Q by using these quantities over here. So the given data is R, mass of water, and initial temperature, final temperature, time is given in 10 minutes, so we will convert these minutes into seconds. So we have 600 seconds and the voltage is 110 volts. Solution for A will be to calculate power. We have V square over R also equals to Q over T. In thermodynamics, rate of doing work, that is joules per second, is given as Q over T. This Q is specific heat, and we know that to find specific heat, Q is equals to mc delta T, where C is the specific heat of water, and its value is 4186 joules per kilograms per degree Celsius. So we put in the values. We have the value of V. We are to calculate resistance over here, and we know the value of mass of water, C, and change in temperature over time. So R will be equals to V square into T divided by mc delta T. So putting in the values, voltage is 110 times 600 seconds, mass is 1.5 and 1.5 kilograms. Sorry, I have written over, this is incorrectly written over here. It should be 1.5, not 15 kilograms, because in the statement it's 1.5. So 1.5 into 4186, and final minus initial temperature, and by simplifying it we get the value of R, which is 28.9 ohms. Next we will find the cost of heating the water. So for that we will proceed as the amount of energy transferred will be power into time, which is equals to V square over R into time, and 110 divided by 28.9 into 10 uh, into 1 over 60. So this is what we get a watt hours. So P delta T is equals to 68.9 watt hour, and if I want to write it in kilowatts, so I get that 0.069 kilowatt hours. So cost will be, if I multiply this with 0 0.100, I get 0.00698 dollars. So this will be the cost of heating the water. So next, in example 27.9, the statement says that in a certain particle accelerator, electrons emerge with an energy of 40 mega electrons volt. So mega is 10 raised to power 6, and if I want to convert this mega electron volts into joules, I will have to multiply this 40 with 1.6 into 10 raised to the power minus 19 joules, and then I get the value in joules. The electrons emerge not in a steady stream but rather in pulses at the rate of 250 pulses per second. This corresponds to a time interval between pulse of 4 milliseconds given in the figure. Each pulse has a duration of 200 nanoseconds, and the electrons in the pulse constitute a current of 200 milliamps. The current is zero between the pulse. How many electrons are delivered by the accelerator per pulse? So we are to find the number of electrons delivered by the accelerator per pulse. So the figure shows that we have current along y-axis and time along x-axis. This is 200 nanosecond is the duration of pulse, and this is the interval between the pulse, that is from 400 from this pulse to this pulse. The time taken is 4 milliseconds. So the given data is energy, that is 40 mega electron volts. I have converted it into joules, and the procedure adopted is this. And next is pulse rate is 250 pulse per second. Time interval between two pulses 4 into 10 to the minus 3 second. Pulse duration is 200 into 200 nanoseconds. So in seconds it is written as 2 into 10 to the minus 7 seconds. Current is 250 milliamps or 0.25 amps. We are to find the electrons delivered by the accelerator. So how many electrons delivered by the accelerator? This is what we are supposed to find. For that we have to find Q as well. So for A, we will proceed as Q is equal to I integral dt, which will give me this time, and this is the time of the pulse. So I have the value of I, and I have this time as well. So Q will be zero point 0.5 into 10 to the power minus 7 coulombs. Now electron pulse delivered is given as 0.5 into 10 to the power minus 7 coulombs per pulse divided by 1.6 into 10 to the power minus 19 coulombs per electron. By dividing this I get electrons per pulse, which is 3.13 into 10 to the power 11 electrons per electrons per pulse. In part B, we are to find what is the average current pulse per pulse delivered by the accelerator. So we will use I average equals to Q pulse divided by T. So as we are to find the average current per pulse delivered by the accelerator, so to find the average we will use time 4 into 10 to the power minus 3, that is the time interval between the two pulses. So we have the value of Q from part A, and we have the value of time, and average current will be 12.5 microamps. In C part, what is the peak power delivered by the electrons? Now we are to find the peak power delivered by the electron beam. So we will use pulse energy divided by pulse duration. Pulse energy is electron per pulse multiplied by energy which we have simplified in the given data, and this is the time for the pulse. So by putting in the value, we get the peak power, which is 10.16 megawatts. Another way to find this peak power is simply by using the formula P is equals to I delta V. So putting in the value for I and delta V given in the data, we can find peak power as well. So both of these formulas are correct. What if the requested quantity part C were the average power? Now he says that instead of calculating peak power, find average power. Then we will proceed as pulse energy divided by time interval between the pulse. So whenever we are to find average, the time we will take is the time interval between the two pulses. So the numerator stays the same, but in the denominator now the time is the time interval between the pulses. So putting in the values and simplifying, and we get the average power to be equals to 500 watts.